Hello, welcome back to the Jerusalem Science Contest. This is our 11th lecture on Chapter 12, Radiation Protection. When we discuss the concept of radiation protection, we have to begin by defining two terms. One is exposure and the other one is dose. So exposure is actually the amount of radiation that's striking an object, the amount of ionizing radiation, in this case, that's striking an object. Whereas the dose is actually going to be how that radiation is actually interacting with the matter that is absorbing it. So, for instance, if we're talking about the human body, we're being exposed constantly to radiation from space, from our own radionuclides that happen to be present inside our body. We're getting a lot of cosmic radiation. We, for instance, get a significant amount of exposure to gamma radiation from space, but nevertheless, the dose that we receive, that is the amount of that radiation that actually interacts with our bodies, is quite small. On the other hand, if we're looking at something like radon, there we would say that perhaps the exposure is fairly low, the exposure to radon, but the dose that we would receive, because the radon would actually be within our body, and all of that energy would actually be deposited within the cells of our body. The dose would be relatively high in terms of compared to the amount of exposure that we were actually getting. So we measure exposure in units called Roentgens, and the Roentgen is equal to 2.58 times 10 to the minus fourth coulombs per kilogram. The coulomb is a unit of electrical charge. I can tell you that an electron has a charge, a very small charge, of 6.241. The coulomb is equal to 6.241 times 10 to the 18th electron. So the electron itself has a charge of 1.602 times 10 to the minus 19th coulombs. So a coulomb is a significant amount of electrical charge. Now, when we're dealing with, on the other hand, when we're dealing with dose, we measure dose in something called either we could be using the gray or the rad. The gray is a larger unit. A gray is equal to 100 rads. The rad is an acronym for radiation absorbed dose, and it's actually, we measure that in terms of energy that is absorbed per kilogram of material. So one gray is actually equal to 1 joule per kilogram. And the joule, if you probably remember, those of you that have had physics, is a kilogram meter squared per second squared is the unit of the joule. So this is actually it's a Newton meter. So the rad is equal to 100 ergs per gram, which is 10 to the minus 2 joules per kilogram, and that's 1 centigray, or 1/100th of a gray. And there's an example in your book where they're converting, the question is a 91 kilogram mass, if it was, how much energy would be deposited by a dose of 1.00 grays, and you can see that that actually comes out to be 5.7 times 10 to the 14th million electron volts. And again, a gray is equal to 100 rads. Now, when we're talking about these doses, we also have to consider that not every form of electromagnetic radiation is going to react with matter in exactly the same way. So we need to adjust the dose depending on the type of radiation that we're actually dealing with. And we use something called Q, which is a quality factor. And it's a little bit like linear energy. When we were talking about linear energy transfer, we know that alpha particles deposit the most energy, followed by beta. Gamma is the least. Well, we've got something similar to that here. And we have something, a weighting factor, a relative biological effectiveness, RBE. And what we do is we can define a dose equivalent. It's the amount of biological damage caused by ionizing radiation. And it's sometimes called the absorbed dose, it's the absorbed dose times this quality factor, and we use the symbol H for this amount of radiation that actually causes this biological damage. So the actual dose then that we're going to be talking about is going to be the dose equivalent, rather, is going to be H is going to be equal to dose times Q. And we're going to measure that in units called sieverts. And 1 sievert is actually, we had the gray, so we say that a sievert is equal to the number of sieverts equals to the number of grays times the quality factor. So for most forms of electromagnetic radiation, relatively low energy beta particles, gamma radiation, these kinds of things generally will have Q values equal to 1. So effectively, if we're dealing with that kind of radiation, a gray and a sievert are essentially the same thing. This is for X-rays, for gamma rays, and most beta particles. But for some low energy beta particles, the Q value is a little bit higher, and also it's higher for beta particles, for instance, having less than 30 kilo electron volts of energy. Q goes up to 1.7. Thermal neutrons have Q values of 5, and alpha particles have the highest Q values, and that's around 20. So we can use those values to actually adjust for the amount of damage that these kinds of materials are going to do. But remember too, with alpha particles, they're only really going to be dangerous if they're internal, if they're actually inside our bodies, because alpha particles outside of our bodies, of course, are not going to penetrate. They're not even going to penetrate the first layer of skin. So we're dealing really, what we're really dealing with there are those materials, alpha-emitting materials, that have actually been absorbed into the human body. Okay, so we've talked about the sievert. We also have a unit used not so much in Europe but in the United States called the rem, which is the Röntgen equivalent in man, and a rem is a centisievert, 100th of a sievert, or 10 millisieverts, so it's 10 to the minus 2 sieverts. And again, we can say if we're dealing with something where the Q value is 1, a sievert is a gray and a rad is a rem for those kinds of things. We can also use something that's called KERMA, and the KERMA is another acronym. It stands for kinetic energy released. Your book says released in media. Most people will say it's kinetic energy released in matter or materials, but media is another way of saying it. So it's another way of looking at dose, and in this particular case, we're actually going to be looking at there could be very, very subtle differences between the idea of KERMA and the absorb of dose. But when there are large amounts of secondary radiation, could be bremsstrahlung, for instance, being produced, some of the energy of the material is we could lose some of the energy of the material. So the two values, KERMA and absorbed dose, might not be exactly the same, but for most cases they are. So if we want to talk about different media, we also have something that's called the F factor, and we can use this to adjust dose or KERMA to a specific medium that the material happens to be passing through. So dose depends mostly on the attenuation coefficient, which we saw in Chapter 5, mu sub m, which actually depends on the atomic number of the material that this happens to be passing through. So if you look, for instance, at page 202, you'll see figure 12.1, and this is actually showing how photon energy can differ for a variety of two different kinds of tissue, which is muscle and bone. And we know that water and muscle are composed of materials, mostly lower Z elements, whereas bone has things like calcium in it, and there's some other higher Z kinds of materials. So you can actually see a difference if you look at figure 12.1. If you look at the plotted on the y-axis is the F factor for water and muscle, and then photon energy. So we find that for photon energies between 0.01 and 0.1 million electron volts, that the F factor increases for bone, and then beyond that level it rapidly decreases. And it's exactly the opposite for muscle, which looks very much like water, like transmission in water. So we're actually seeing that the dose is going up for these low energy particles in bone. Then for the higher energy it goes down, but it goes up for water and muscle. Okay, so these again are just different ways that we have of actually adjusting the doses that we would receive. There is the Nuclear Regulatory Commission actually sets. It doesn't actually set the regulations. The regulations are actually set usually by the National Council on Radiation Protection, the NCRP. Will at least make recommendations in terms of how much exposure, for instance, workers are allowed to receive. And the Nuclear Regulatory Commission, although it is responsible for controlling the distribution of radioactive materials, it really only can make recommendations in terms of, the NCRP makes recommendations, and then it's up to the Nuclear Regulatory Commission to actually enforce these kinds of things. So if you look at table 12.1, which is on page 203, you'll see a number of different effective dose limits that are recommended by the NCRP. And you'll notice that they go from about a half of a millisievert up to a maximum of 500 millisieverts. And it just depends on what we're talking about. So for effective dose limits, the annual recommended is no more than 50 millisieverts, and for a cumulative dose limit, it's 10 millisieverts times your age. So for instance, that would mean that someone who was, let's say, 60 years old would have a cumulative dose limit of 600 millisieverts, or a tenth of a sievert. Equivalent dose for various organs. The lens of the eye is more sensitive than the skin, hands and feet, and can receive an annual dose of 150 millisieverts only, whereas the skin, hands, and feet can receive 500 millisieverts. And 500 millisieverts seems to be the limit for also for emergency occupational exposure. This would be a situation where someone had to go in and rescue someone from a radiological accident. We would only allow someone to be exposed up to a half of a sievert during that kind of because that's a fairly significant amount of radiation. It's a non-lethal amount of radiation, but it is an amount of radiation that without proper protection is going to cause some damage to tissues. Public exposure levels are set very, very low. Millisievert for frequent exposure, 5 millisieverts for limited exposure. Again, some of these limits are quite low, and for a pregnant woman where the fetus might receive exposure, that's limited to 0.5 millisieverts. Now these levels are extraordinarily low, because if we actually look, I'm going to move a little bit forward here to page 204, where it's going to show you in rems or sieverts how much exposure a person could get, and what kinds of damage they might expect from that. So anything from 25 to 50 rems, which is a quarter to a half of a sievert, we start to see measurable biological effects. And this usually affects blood cells. So we'll see erythrocyte and leukocyte, that's red and white blood cell counts, will actually be decreased. And there could be some temporary sterility, but generally people recover from this level of radiation. At 200 rems, which is 2 sieverts, reversible bone damage occurs, nausea, vomiting, fatigue, and hair loss. And some people actually do die from this dose, a dose of 2 sieverts. 4 to 6 sieverts, they give you a 50-50 chance of survival. Bone marrow function completely ceases, but it's possible, and there's also severe gastrointestinal distress, and that usually takes place almost immediately after exposure. People that are exposed to those kinds of levels, even if they survive, are going to become extremely sick. They're going to be vomiting, and anything above that, 700 sieverts, almost everyone dies. 700 rems, 7 sieverts, almost everyone dies. 1,000 rems or 10 sieverts, death occurs within 1 to 2 weeks, and at 20 sieverts, death can occur in a matter of hours. So these kinds of levels of radiation are very, very extreme. But there are instances when people have received that level of radiation, and I wanted to talk about that as well, and give you a couple instances where people have received these very, very high levels of radiation.